Steve, you shouldn't take pictures this early in the morning.
Yeah, sorry?
You shouldn't take pictures this early in the morning. Wait till later.
It's all in order. They're all over that.
It's all blurry anyway.
Welcome to this OpenSFS EOFS Breakfast panel on file system. So the agenda of this panel, I am not the go-falter. We don't know where is the go-falter. Go, please, if you can come to unite. I am the shadow speaker. So first we will have an introduction from Norman of OpenSFS, after an introduction from myself. We have a keynote speaker, which is Mark Seeger, and after we'll have a panel discussion. The member of the panelists will be Eric Barton, Peter Bryan from Daratech, everybody knows Peter Bryan, Fellinger from Data Direct Networks, Ken Claffey from Daratech, just near Peter, Hugo, still not there. Brent Goddard from OneCloud, myself from EOFS and CDA, and Norman Morse from OpenSFS. So, Norman, you want to come to the next one?
Thanks. I'm trying for this to be very short, so we'll go through the slides. Just some background information. What is OpenSFS? It's the open source file system community, which we currently estimate maybe 60 or 70% of the top 100, taking control of its future. As you know, we're going through some rocky times. So the community never once ever again to find itself at the mercy of the business plans of the for-profit organizations. So OpenSFS is the instantiation of the community taking control of its future. I'll list something that differentiates OpenSFS. It's been from the very beginning our intention to have dues at a level that we would have enough funds that we could finance the changes that the user community needs in the system. So that's been our goal. We're currently running at about $3 million a year, and we're hoping to see that increase. So again, our end goal is the continued evolution of the robust open source systems for the HPC community. We do our business through working groups. All of you that are participants in OpenSFS are welcome to join the working groups. Depending on your level of participation, you can actually propose and lead working groups. So these are the working groups we currently have. I hope everyone in this room is participating in one of the working groups, making your requirements known, what changes, what improvements you need in Lustre, what additional support you need. Recruiting is going pretty well. Here's one of our latest events in recruiting. So Intel has joined OpenSFS. We're very pleased by that. I don't know if we can announce that or not. Can we announce that?
Yeah, we can announce that.
Okay. So I was hoping I wouldn't have to take that back. Here's a list of our current participants at the various levels of participation. Please forgive me if I left off someone. I did these about 2 o'clock in the morning. That's my excuse, and I'm sticking to it. And also, there's a small possibility that I've made an announcement here. What we try to do is let people who join the organization announce their participation in the organization. So I may have jumped the gun on some of these, but as you'll notice, we have also listed the first name of our board members by their organization. And as you can see, we have several other participants that are doing due diligence and just almost completed the joining process. So I'm going to let them make that announcement. But the bottom line is, the community sees the value of this. I think the Lustre system, ecosystem has been stabilized, and everybody's pleased about that. So we're sort of moving on from trying to stabilize the environment and getting on with our business, which is a good thing. Also, we're very pleased about the relationship between EOFS and OpenSFS with JC and Hugo. So we value that relationship, and as you can see, it is a close working relationship, and it will continue in the future. So we actually have several contracts underway. As I said, we're spending on the order of $3 million a year for current contracts that are doing code development, code improvement, and paying for the support of the Lustre tree. We're sharing that responsibility with Plan Cloud. So we went over this in detail in the birds of the feather session. I'm just going to skip through this. We also have identified the next round of improvements that the community wants in the system. The way this works is the technical working group requests changes. The changes are put in a list. They're prioritized by the community, by the technical working group, sent up to the board. The board is all managers. They don't know what's going on in the technical stuff, so they just pretty much agree with what the technical working group says. So this is the next layer of improvements that we're scheduled to let contracts for. We let contracts to the people in the ecosystem who do actual code development, that's architects, people like that. Indiana University has a contract. So again, these were gone through in detail yesterday, so I'm going to skip through. So I maintain that this organization is essential for the user community. It's really important for us not to move back into the environment that made us all nervous a couple of years ago. So even though it looks like everything's running smoothly now, we lose sight of the fact that this model of having a corporation that represents the user community, or corporations, including EOFS and others that are being formed now, is very important for this ecosystem. We can't lose sight of the fact that if we allow a single company to get control, bad things can happen. So the user community needs to protect its interests by continuing to support these community organizations. So what I'll say is it's been an extremely successful year. Some people have made the statement that the stabilization of the Lustre community is the most important event in high-performance computing in 2011. It is very stable. Things are running well. Good working relationships. Community is defining the changes and improvements they need in the system. We found a way to fund those, letting contracts to people who have the resources and the knowledge and capability to implement those changes. But we can't lose sight of the fact that even though it's been very successful, it would be easy to fall back into the undesirable infrastructure that we've all seen. So we got to prevent that from happening. So as our recruiting poster here says, if you use Lustre, the community needs your continuing, we need your participation, we need your good ideas, we need people to join the working groups, make your needs known, help us prioritize improvements that are being proposed for the system. We need need your good ideas, and we definitely need your financial contribution so that we'll have resources, funding, to hire the changes that the community needs from the people who are capable of producing those changes. So, please join us and contribute to the continuing success of the user community. So, that's my presentation. Thank you.
The European Open File System Association. So here is the list of our members. So now we are close to a little bit less than 20 members, and we have other companies that want to join us. So that shows you that the Lustre community is still very strong and very large, and that's a good thing. So we have many people that can help us to work on open source parallel file system. So the activities we had during last year and this year, in 2011 we participate to the so the Lustre users group. We also had made the breakfast session last year in ISC, in which we signed the agreement with OpenSFS, in which we decided to work together closely and to make the Lustre community a single entity. So just after this event, all the other events organized around Lustre and the parallel file system were jointly made by OpenSFS and EOFS. Mainly when it's in US, OpenSFS organizes, coordinates the effort. When it's in Europe, EOFS is coordinating the activities. So you have we have made two workshops. The first European Lustre workshop, which now is named LAD. I will cover it later, and it will arrive every year in Europe. We also made the third Lustre Developer Summit. So this summit is an invitation-only summit in which we invite all the Lustre developers and put everybody in the same room and try to discuss on what we should do on Lustre, what we will do on Lustre. So really development, high-level development oriented, and make the community work really together. Also, we have on ISC, on OSC, we animate a booth. So you are welcome to our booth. We have a digital area. Also in 2012, we have started an Exascale.io workshop initiative, Exascale.io initiative, originated by Peter Brown. So Peter will cover it later during this morning. And 2 days we have organized a different workshop together, user needs, and what we should do for Exascale. So now just a little some communication, our next event. So the next event on Lustre will be the LAD. The LAD is Lustre Administrators and Developers Workshop. It will be organized in Paris in September, in a very nice place with a very nice social event. So the registration is open. So if you want to come, you're welcome. It's a good place to the Lustre community. Also end users, sysadmin, and also Lustre developers, so we can share many information together. Okay, so now, that's my last slide. I would like to introduce Mark Seeger for his talk on Exascale. So Mark, please.
Intel. Since then, we've been very active in figuring out a strategy for Intel around exascale, and I'd like to talk to you a little bit about our thinking. But the bottom line is that we see a big intersection between big data, but not the cloud, but what we call fast data, which is HPC storage. So that's kind of the message of my talk there. We're targeting an exascale machine in the 2018 to 2020 timeframe, and to contrast this activity from the way Intel has approached supplying component parts to the ecosystem in the past, we're taking a systems view to this, and the Lustre parallel file system is an integral part of that strategy because it's a open source, community developed thing, and it also enables us to have the IA architecture in the storage platforms as well as the compute platforms. So in heading to exascale, our design focus is enabling end user applications, and there's only three basic problems to get there: scalability, scalability, and scalability. So there's the hardware scalability. Our approach there is to have a simple node as possible and have as many of the functions that are typically on the motherboard and in other parts of the chassis or racks on the processor, integrated interconnect, and keep it very simple. The MTBF needs to improve by about an order of magnitude, or what we project will be the standard Intel roadmap. In addition to that, we have to improve power consumption by over a factor of 2 in order to get it within the envelope here. Another thing that is a distinct change for Intel as well is scalable software. We currently are mostly in an enabling role in terms of software on platforms, but with the exascale system, there's a very strong interaction between the system software and the applications and the hardware. So we're taking a hierarchical systems approach to the system software. Basically, it's an idea where we take a very hard problem, which is have a full operating system on 100,000 nodes, and we solve it into two problems. One that is merely difficult, and the other one is a solved problem. And the merely difficult problem is function shipping off of the compute nodes to the operating system nodes, and then having a standard Linux distribution on the operating system node with the Lustre parallel file system client there. And then the scalable applications is a critical part. It's anticipated that the exascale machine will have over 1 billion way parallelism. So what we're thinking about there is asynchronous communications and I/O, as well as enabling applications to do data transfers in a method that is fundamentally theirs. This is our projected software architecture for the exascale platform, and again, Lustre is a key component of that. And the message here is that we're not forgetting storage. Storage is a major part of the overall system exascale strategy. One of the things that I noticed while working at Livermore was that the usage model for applications is changing rapidly as we went through the terascale era into the petascale era. And one of the fundamental shifts is that they're not just running one application anymore. They're actually running what we call a quantification of uncertainty framework, which drives a bunch of application instances on the machine. Of course, there's the very large application run that takes the whole machine and runs for months on end. But then there are a series of runs that are much smaller that explore the parameter space of the application area in order to quantify the uncertainty. So it's no longer good enough to get the predictive simulation answer, but you have to also be able to have some indication of what the sources of errors are in that simulation, how big those errors could potentially be, how they impact the solution, in order to inform the scientists about what their confidence in the solution is. So if you're going to make predictive simulation guesses and then make bunch of applications, and those applications typically use a POSIX parallel file system, but they, in order to keep track of the massive amounts of data that they have coming out of their application, they put in a parallel database within their application. And that allows them to have objects that are in the application and then turn that into block I/O. And then they go to the block I/O through the POSIX layer and then down to the block servers. And all of the block servers today are being implemented as object servers on the back end. And those object transactions with the devices. So we have object at the top, objects in the middle, and object at the bottom, and they're not connected. So the aha here is, hey, let's take the objects that are in the application and drive them all the way through the stack down to the device. Now, there's a fundamental change that has to happen here. Two fundamental changes that have to happen here. One, we need a different interface besides POSIX. Okay, everybody willing to give up POSIX? Raise your hands. Okay, well, it turns out the application guys, when I go over and talk to them, I say, this POSIX interface that was designed in the 70s, it's been pretty good so far, but we're running out of gas with it. How about we do objects instead? They go, we've been asking you guys for object interfaces for the last 5 years. Where you been? I mean, it's not like there's a resistance to this. It's like, come on, guys, get on with it. The other fundamental shift that has to happen is that down there on the block device, we need to be able to have user-defined objects transacted with the device down there. And so that means that the device needs to be adaptive to the application as opposed to have a fixed object or block size down on the device that ripples through the stack and requires the user to conform their data types and so forth back to their internal data structures. The other thing, when I first started thinking about it, I go, oh my God, how are they going to see their data? Typically what happens is people log in and type ls and look at the directory and then go cat files and all that stuff. Man, that's so 70s. That's not what people do today. Scientists today have their data analysis stuff typically written in Python. So the first thing they do when they log in is that they Python, Python, get inside the interpreter and then read all their data into Python in a single system image, right? Which they're limited in size of the data that they can pull in because they're in memory. And then they run scripts on their objects that are now in memory in order to do the data analytics that they require. Why don't we just provide them with a database mechanism that allows them to search and to compute on their objects, not in memory, but in a distributed infrastructure. So it maps very well into what users are already doing. So it's like, the storage community here is actually catching up to where the applications guys are. The other thing is that there's a need for checkpoint restart in these applications. So the green instance here is a series of computations that take place over time, and then the red here is the I/O, defensive I/O for checkpoint. So typically what happens is that all of the computation in a parallel application takes place a couple of time steps, maybe 4 to 8 hours of computation, and then the application takes a checkpoint dump, and then they go back to computing. But what happens is there's an implied synchronization point at the end of that computation, and then again at the end of the I/O, and that happens over and over and over again. And when you're computing, you're not doing I/O, and when you're doing I/O, you're not computing. And so right here, we're wasting the computer, and over here, we're wasting the I/O subsystem, right? And so there's a zero bandwidth required, and then there's maximum bandwidth required, and then it goes back down to zero again. So that's probably the worst possible way to use a parallel file system. Instead, if we had an object model where users could transact their objects with the storage mechanism, notice I didn't say file system, they could start transacting the persistent objects way far in advance in their computation and overlap the computation with the I/O such that when all of the the transactions for an epoch were complete, right, then a new epoch starts. And look what happens. All of that computation and I/O gets compressed down into only computation. So overall, the application runs much farther. And the red part here is the connote that the amount of data being transferred is the same. But what happens is because you're doing it over a much longer period of time, the peak I/O rate goes way down, and you're using the I/O subsystem most of the time, which is a much better way to utilize the storage mechanisms. So overlapping computation and I/O, and the synchronization is reduced. So that wiggly line there is a way to indicate that as soon as this epoch is complete, the computation can proceed. Now, so every individual task doesn't have to synchronize with all the other ones. There's a very loose synchronization that can take place here. It doesn't give you minutes or hours of slop, but it gives you tens of seconds of slop, and that's exactly what you need in today's and in future computing models. Now, those are the challenges of high-performance computing for exascale. What I'd like to shift to for a couple of slides here is the big data challenge. The amount of data coming out of the internet today is absolutely astounding. These numbers here are unbelievable. It's only the beginning. In fact, IDC storage capacity growth is shown here. The public cloud content thing has a compound annual growth rate, or CAGR, of almost 50%. That means it's doubling in less than 2 years. The public cloud content is almost 60%. The traditional replicated data is a 30% CAGR. Traditional unstructured data, which is archives, is about a 60% CAGR. And the typical structured data, enterprise databases and so forth, is about a 30% CAGR. These are phenomenal growth rates. If you think about where high-performance computing growth rate is for processors and stuff, it's in the 10 to 15%, which is a great growth rate, but these far exceed it. So this market is exploding. And these are the sources of the data and some indications of the sizes here. And again, 7 exabytes of traffic data used by mobile users worldwide in 2011. I mean, one of the criticisms Intel has had up till recently, where's your phone? The computer market is moving toward phones. It's not really. With all that data being transferred back and forth, there's really a large server back end driving all those phones, and that's where the big money is in that. So the grand challenge here is with this massive amount of data that's coming through. How do you get knowledge out of that? In this community, there's a perfect example of this with the Target stores, where they were tracking people with their preferred shopper cards and their buying behavior, and they figured out that there are 3 times when people make changes of buying habits. One was when they got married, and another one is when they have kids, and the third one is when a family member dies. So they identified mechanisms by watching buying behavior. They could figure out when a couple got pregnant, and they could even predict when the baby was going to be born. And so they did targeting advertising for baby stuff and got people to change their buying habits to buy more, and Target and doubled in-store volume. Doubled. It's amazing. So there's a lot of money to be made commercially by getting information and knowledge out of these big data. But the problem is with the exponential growth here in data, the budget for IT spending to deal with that is a much lower CAGR, which means that there's innovation opportunity there. So by taking data and thinking about it in terms of getting information out of that, and then prioritizing that information and helping decision makers make decisions, that is the ultimate goal here. And if you think about high-performance computing in the UQ scenarios I was talking about before, what we're trying to do there is create a lot of data and provide information, predictive simulation capability, so that scientists can make decisions. It's exactly the same paradigm. So there's a lot of overlap between what we're trying to do in HPC and what the big data folks are trying to do with all that data out there. So there's been one model out there that has captured a lot of mind share. That's Hadoop. It's a map-reduced data parallel model, and as long as the mapping and reducing steps are well balanced, the tree is well balanced, and you do the computation where the data is, it runs very well. If you have an unstructured mesh, though, like trying to figure out the circle of influence of a particular Facebook user, for example, and what the interactions between those circles of influences are and so forth, that's a very unstructured computation and doesn't map well onto the MapReduce framework at all. And so what we're looking at Intel Labs and with Carnegie Mellon University is methodologies for doing in-memory graph traversals to identify these connections and figure out new connections from that aren't obvious from the data. The problem is it's unstructured, right? And so what we really need is an I/O mechanism where these guys don't have to bring all of that unstructured mesh, unstructured data into a single computer memory. And so what we're talking about here is the moral equivalent of out-of-core solving of large matrices, right? And so what we want to be able to do is an out-of-core solution using the file system as a caching mechanism to have a very large unstructured database. So to do that, we're working with WAN Cloud to peel back the Lustre POSIX interface and get at the object infrastructure underneath it and define this new thing called the Distributed Application Object Service, which is objects defined by the end user applications that works at the scales all the way to exascale and separates the scalable object namespace and allows the application to define metadata for the objects which are searchable and then have application data in the object which is the scientific data that's not searchable. It gives us a high level of I/O. So if you think about it, if we have some kind of persistent storage, either on the compute node, or if you remember back to my exascale diagram, system architecture diagram on the OS nodes, there's a very fast transaction mechanism between the object, the user application, and a persistent storage on the computing device, and then that later dribbles out to a centralized storage mechanism. This is the infrastructure that could allow us to have that very fast transaction mechanism. Oh, and by the way, since it's based on the base Lustre infrastructure with a new Deos POP API on top of it, we can co-locate the data on the same devices. So you can have a Lustre parallel file system, you can have a simulation data with an object database on top of that, and oh, by the way, we can map the Hadoop file system and MapReduce infrastructure on top of that, and we can also use that for unstructured calculations as well. So if you go and talk to enterprise storage guys, there was a big revolution in storage in the 2000, early 2000 era, which was basically consolidating multiple devices into a virtualized SAN environment that basically shared devices, but it didn't share data. So now what we're seeing, and that was done with mainframes and custom designed RAID controllers. Now what we're seeing is a commoditization of that market, both on the mainframe side, but on the storage side as well. I/O servers now are predominantly software-based and based on the IA architecture. And what we're seeing is the application servers are also IA-based and virtualized and those kind of things. So now we have a unified network, a distributed application storage and metadata services. And what we see in the future is that we can virtualize that environment. And there's a big wave of virtualization that's already happened on the application server to utilize the idle cycles in the enterprise. And the HPC, we don't have that problem. Every machine is saturated as soon as it hits the ground. But on the I/O side, we can also virtualize the storage servers. If we virtualize the storage servers, we can, in this distributed application object storage mechanism, we can also distribute methods to operate on those objects at the storage server. And if we do it in a virtualized encapsulation environment, we can impose the right locality, we can impose the right security model and protection safety model for the RAID controller software underneath it. So I'm very excited about extending the computing paradigm from one where in high performance computing we always suck all the data back to the supercomputer to do the data analytics and visualization and stuff, to one where now we can, if it makes sense, if it's data intensive, we can move the method to where the storage is, like Hadoop, except it's unstructured and has an arbitrarily connected graph type structure, versus always being forced to move all of that data back to the supercomputer. So in summary, I think that exascale requires a different HPC storage paradigm, and the users are demanding that that be an object-oriented paradigm, object-oriented paradigm where they get to find the objects, not the file system or the devices. Big data and fast data have very similar requirements, and their objectives are very similar, and that market is growing extremely rapidly, and so that's got a lot of vendors very interested in developing technology in that area. And if we can overlap that with the requirements of big data and fast data, I think we can go forward to exascale and have HPC be the leadership position in defining the technology that is used by both camps. And now we have a much broader marketplace upon which we can base our economic underpinnings of the drivers, the technology drivers for HPC. So let's go fully object-oriented, and the time to do that is now. So that's my talk. Big data intersecting with fast data. Thank you.
Thank you, Mark. So, I'd like to introduce you, Hugo Falter, EOFS Director, that will be the moderator of the panel. Maybe you can answer the first question to Peter, because it's already history.
Good morning, everybody. So we have some questions here. The first is, we would like to hear from Peter what the actual status is for the exascale I/O work. Peter.
I brought a few slides to tell you about an initiative that was started late last year, and we have followed the usual struggles finding a name and come up with something that was still available, so we called it the exascale I/O work group. So the mission of this work group is quite well described and has stayed the same. We wanted to gather requirements from primarily application developers to learn what future I/O systems really should support. That requirements gathering has happened, and while our conclusions have a very large overlap with what we just heard from Mark, there are also areas where I think we've heard much deeper wishes, and in some cases I've heard a lot of criticism. I've worked in the storage industry, and Quadricator was told, stop doing what you've done before because it hasn't really worked all that well. So we are going to proceed now designing the architecture based on the requirements, implement it. It's a completely open effort that we target is a middleware effort, so that it can run possibly on Lustre as an infrastructure for storage of data, or it can run on a new system. We did not want to prevent in any way that vendors would build firmware or hardware or open projects to support the EIOW. It's definitely going to be a next generation element, although we've looked at POSIX and there is some need for some POSIX interfaces here and there. I'll tell you a little bit more about what we see happen. So how have we approached this? We became, before the first meeting we held, an EOFS supported work group. This seemed just like a good thing to do to get a framework and that sort of thing. We've chosen a process, so we are not following a research approach where we look at every problem as something that still needs more research. We follow the industry standard requirements gathering architectural design process. It's called the architecture-centric engineering process from the Carnegie Mellon Software Engineering Institute. There are many members, so we held meetings, and I think we have seen a total of 40 to 50 different organizations attend our meetings. So that is actually like more than double the membership of EOFS and OpenFS. And we also got many apologies from people who say we would really like to be involved, but we can't make it this weekend or something like that. So I think it's going to be a fairly large group. Europe was overwhelmingly present. I think every big institution in Europe participated in some way. In the US it was nearly as good. There was just a handful of big organizations that somehow couldn't make it. We got a few key Asian players involved, but that was somewhat smaller. The agenda for 2012 is, of course, halfway done. That's the end of June, more or less. So we held the 3 requirements meetings we said we would hold. We held one in Europe, one in the US, and one in Asia. They got progressively, by the way, harder because we had longer introduction to the previous work. We now have a small steering group, which is chaired by Hugo, and I'm acting as the secretary. And we have 3 work groups that look at the API level, the storage level, and the RAS interfaces of this new system. We expect that these work groups are going to be developing the architecture following this process, and that we will be inspecting the architecture late in the year. Inspecting an architecture is extremely important. Did you actually architect something that meets your requirements? That's one good question to ask. The second good question to ask is, did you architect something that can be implemented? Yeah, is the architecture clear enough? So before we proceed beyond architecting, we will hold these analysis sessions. What's very exciting is that many research projects are now beginning to spring up around the world to leverage this work and study if it can solve particular problems in ABC or big data. So the interesting thing is, many people, of course, keep asking, so should the next system be Lustre? And I would be the last person to say that Lustre shouldn't be successful or something like that. But it's not going to be the last file system, or the last storage system. There is going to be a moment that we need something else. I don't know if that is the moment of exascale, if it's sooner or if it's later. And it's certainly the amount of progress in the Lustre community is sometimes very impressive, and it makes you think like, wow, this thing will scale another factor 1,000, so we're good. And at other moments you feel like, boy, it's been very difficult to drag it forward. But I don't think it will die. It's probably beyond the point of death just through wide use, and so like fat, it's going to stick around. There are billions of fat file systems in your phones these days. But something new is going to come. And the new thing that I think is really going to come touches in a much broader view on what Mark was just saying. A future storage system is going to make all file systems that we have today look like the pre-SQL phase for databases. If you go back to the 70s, databases were huge programs that were all built from the ground up with proprietary interfaces and so on. What we've heard very, very clearly from the users and the application builders is they want a toy language, a data management language to construct storage infrastructure. Some people want this, other people want that, and this is exactly the sort of problem that SQL solved for databases, and that hopefully EIOW will attack for large unstructured data. Yeah, so there won't be a close analogy to SQL, but there will be some language and building mechanism coming out of this that enables a very wide variety of people to manage data at a large scale. The details may have a very large overlap with what we just heard from Mark Seeger. I think this is my last slide. Thank you very much.
Thank you, Peter. Any questions? I have some questions. The next one is to Eric Barton from Cloud. What is necessary, Eric, to scale up to exascale? What is necessary for a file system?
How long have you got? It's a big question.
I know.
But it really means you've got to look at the whole stack from top to bottom. And it's something that we're starting now. Many of the components Mark's just described. I think some of the components already exist in Lustre. The underlying object storage in Lustre is a major component. But as these systems grow larger and larger, you start having levels of functionality in which one level's data is the next level's data plus metadata. And so you need a top-to-bottom transactional model that will make large systems tractable. Clearly, applications need to interact with the file system in more scalable ways. I believe that I/O APIs are going to become, for a start, less stream-based, obviously, much more to do with describing distributed data structures, instantiating them, persisting them. But also, APIs are going to have to become much more asynchronous, just like communications APIs are already. And so there are going to be many different APIs, I'm sure, for different application areas. But underneath it all, I think we can have a fairly common infrastructure for the baseline object storage. In the middle, there's a crucial missing piece, which is where we have to match the fragmented data structures that applications instantiate. We want to allow masses of tiny fragments of data to all be aggregated together and then shipped to central storage. So some method of aggregation, some method of placement in order to really treat the file system much more like a streaming engine, but with large amounts of more temporary storage near to the application to allow the relationships between the data to be fully explored. So it's a big question, and we're tackling some of the major issues. We've been talking about this now for several years, and we're getting ready to start actual work on all levels of the stack. At the bottom level, with the object model; in the middle, to do with data layouts and aggregation; at the top level with new I/O models.
The next question is to Brent Gorder from Cloud. How important is exascale for Cloud? Is it on your agenda? Is it playing a significant role?
So in the US, there was a recent call for proposals called Fast Forward. And we decided to put all of our wood behind our proposal here, and I sent a message out to the companies saying that let's spare more effort to put this proposal in place, because exascale is the future of what we have to do for the community. We turned in a proposal at the end of May, I think it was, and we are highly optimistic
question to Dave from DDN. How can we improve storage efficiency?
I think that there's a lot of effort placed into communication, interprocessor communications, communications between nodes. So there's been a lot of effort devoted to that. There's been a lot of effort devoted by Intel and others in the bridge structures. But I think if you take a look at the way data is still being handled and even into the future, we're still dealing with, for the most part, SCSI down to the very lowest layer. And maybe exascale is the time to start thinking about whether we want to re-examine the small computer systems interface and take a look at that in detail and see exactly what has to happen to move data. We're still moving data with 2K frames. We're in the fastest again infrastructures. And I think what that's doing is it's causing the need for staging. It's causing the need for data copies just because you have some very slow layers and some very fast layers that you're trying to merge. And I think they need to be brought into one infrastructure. And I think that would include the necessity for first, a more efficient data placement model. It's not only object-based in the addressing side, but object-based all the way down into the actual media side, where today we're still using expense-based file systems. We're still basically file allocation tables still look pretty much like DOS. So maybe it's time to re-examine that too. Maybe it's time to take a look at actually how data is placed on the medium and to maximize the payload to protocol ratios necessary to actually place data. I mean, block sizes are still relatively small. Maybe in exascale, we should start looking at addressable block sizes that are a meg, 2 meg, 10 meg, something that makes more sense, removing the size of data we're moving, and also build metadata infrastructure that is efficient. We kind of gone with tradition in terms of that final data placement step, and maybe it's time to start to look at true DNA conveyance of data, and we don't have the luxury anymore at exascale of just assuming that everything below a certain level works. I mean, some of you have in fact, I'd like to see a show of hands. How many of you have ever written assembly language? Ah, good. Okay. So you count machine size, and I think at this point in time, we don't have the luxury of just assuming that higher level abstractions are going to solve our lowest level problems. If we waste a millisecond and over a billion operations, that's 11.5 days. And I think so we don't have the luxury anymore of something that existed. I think what we need to do is to nail down again some detailed infrastructure on the back end, and then the higher level abstractions that have been discussed today work even better.
Thank you. Ken from Cyrotex. Do you see any kind of revolution going on in I/O?
Thanks, Hugo. I think it's going to be clear for me from today's panel that there's probably a revolutionary and an evolutionary path. I think a couple of things are pretty clear at this point in time, particularly as we look forward to exascale. I think we can argue that 5 years away, 10 years away, is longer. It's probably too early for anyone to really commit with a definitive view to say this is the path we're going down. I think from a design perspective, we can like to look at it that there's an evolutionary path and a revolutionary path. Those paths will continue to diverge, those paths will come together. I think what's important for us as a community is that we approach this unemotionally, stand back and be open to new ideas, and certainly let's explore those new ideas and new ideas. If we're going with a linear approach, we're probably multi-year that we'll probably end up failing. The future definitely will be
Yes.
So, I guess one for Lustre people. So which bits of Lustre that exist today are going to be really good supporting these object models we've been talking about? So the POSIX front end currently, that needs to be modified. The back end is currently not based on objects. Which bits in the middle are good and which bits need the most attention to move an object-based model right?
So we looked at that in some detail, and about 70% of the code base is actually reusable in the new model. And that's like standing on the shoulders of giants, because there's been 10 years of effort, $100 million or more dollars of R&D investment by multiple entities put into that infrastructure. So the object storage backend is reused, the communication layer is reused, the failover mechanisms are reused. What we take away is the metadata server and the client and POSIX client, and implement a different client and indexing mechanism with the database. So there's a huge amount of reuse, and by the other piece of leverage that we get through that reuse is that we can actually coexist the POSIX parallel file system with the new object-oriented database approach on the same devices and share, not share objects, but at least share the devices and allocate storage between them on a dynamic basis. So I'm very excited about the possibility in that model of having a gradual transition out of the old mechanism into the new mechanism as demand for the new mechanism and applications adopt the new mechanisms takes over.
Any more questions? If not, I would like to use that opportunity to just say thank you. Question?
Yeah, sorry, I just want to add one more thing, which is that I think it's essential that we reuse components like this because of the amount of engineering effort involved in not just prototyping functionality, but actually getting to the point where it can be deployed in production. And stability is the most important thing that you want out of a file system, practically. In fact, this file system is the resilient strategy for the rest of the data center. So it's really important that we get that right, and therefore we have to have a long-range architectural plan with sensible periods of life for stabilization and production.
Any more questions? Well, actually, we are at the end of this early breakfast meeting. May I just say thank you to all of you coming so early to this event. You showed another time how important I/O is. Was there a question?
I just want to thank Eric for mentioning stability and reliability. I think one interesting thing about the MapReduce environment is it addresses both the computation and the reliability model of that computation. And so I think for exascale for me is not scalability, scalability, scalability. It's reliability, reliability, reliability. And so I was just curious if you want to say a few more words about what you're going to do to spark some innovation in the storage stack to address that.
Yeah, but in order to address the reliable issue, you have to build scalable structures. No, but I kid you not. One of the things that was kind of left out of Lustre really was the global reliability model, and the full model of Lustre today is things happen to individual servers, and that's to go away. That's to be sort of global awareness. We need that anyway for the transaction movement, so it's all back to the same problem.
Okay. Finally, any questions? No? So, let me go back to what I wanted to say at the end of this morning. Thank you, everybody, for coming to this early event today. And let me say thank you especially to Norm and to Chacha. What you contributed with your teams in OpenSFS and EOFS the last 2 years was outstanding. Without you, I think Lustre would be in a much worse developer side as well as from those who show up at Lustre user group and the workshop in Paris. You do a contribution to keep Lustre